I've got a little something on the desk in front of me, and if you can, do it too, at home, right now. Find a paperclip, an ordinary paperclip lying flat on the table, and a fridge magnet, the cheapest, saddest one you own, the bent little thing that's been holding up a takeaway menu since forever. Now hold the magnet a short way above the clip, not touching it, just near. Hold it there in the air and watch what that paperclip decides to do.
It jumps. It doesn't hesitate, doesn't think it over, doesn't weigh up its options. The clip leaps straight up off the table and slaps onto the magnet, quick as a blink. And in that one instant, that tired little magnet off your fridge just beat the entire planet Earth in a tug of war. And it didn't even break a sweat doing it.
Hang on, the whole Earth. The entire planet was pulling the other way.
The entire planet. Every last scrap of it. The whole enormous mass of the Earth reaching up through the table and hauling on that one paperclip, pulling it down toward the floor with everything it has got. That's gravity, the Earth holding the clip. And against all of that, the whole planet on one side of the rope. You've got a single bent magnet the size of a coin, pulling up. And the coin wins. The clip goes up. It isn't even close.
That is genuinely strange, once you slow it right down. I do that 100 times a week without a flicker of thought. Slap a note onto the fridge, and I never once notice I'm out-muscling the entire world with a scrap of painted metal.
You out-muscle it every single time, and you never notice. And here is the thing I want you to sit with, because it's the whole hook of the night. Gravity is not some feeble little afterthought of a force that nobody respects. Gravity is the one that runs galaxies. It's the one crushing the hearts of stars until they catch fire. It bends the paths of the planets. It holds you flat to the ground every waking second of your life. It's the force you actually fight. The one you push against, groaning when you drag yourself out of bed in the morning.
Right, it's the one I can feel. It's the one with a body count. I have never once had to wrestle a magnet to stand up in the morning.
You never have. And yet, and hold both of these in your head at the very same time, because the two together are the whole puzzle. That mighty, planet-shaping, star-crushing, bone-tiring force loses, instantly, without a fight, to a magnet you got free with a takeaway. And there's only one thing that can possibly mean, and it is a strange sentence to say out loud. Next to the other forces of nature, gravity is almost nothing at all.
Wait, no. You're telling me the force that makes me groan getting out of bed, the one that finished the dinosaurs' very bad afternoon, the one holding the actual moon up in the actual sky, that one is the runt. That's the weakling of the group.
That is the weakling. By a margin so ludicrous that we're going to have to spend a good chunk of tonight just trying to feel how big it is, because your mind will keep trying to shrink it back to something sensible. Gravity is the single feeblest force there is, by a distance that stops being funny and starts being a little frightening.
Okay, but you've just walked me straight into a wall, and I think you did it on purpose. Because if gravity is the runt, if a bent fridge magnet openly laughs at an entire planet, then why on earth is it gravity that runs the universe? Why isn't the whole cosmos out there being shaped by whichever of these strong ones is doing the winning?
There's the knot. And it's a beautiful knot. Look up at the night sky. Really look at it. And everything you can see, every star pinned in its place, every galaxy wound up into its slow, patient spiral, all of it is being shaped and held by gravity. The runt, the weakest of the four. And meanwhile, the strongest force in all of nature, a thing so mighty it makes gravity look like a rumour of a force, is nowhere to be seen up there. It shapes nothing in that sky. Not one star, not one thing.
That's backwards. That is completely backwards. The strongest one does nothing at all on the big stage, and the weakest one runs the entire show single-handed.
Backwards is exactly the right word for how it feels. The weakest force writes the whole story of the cosmos, and the strongest force sits the whole thing out in silence. And the answer to why that happens is honestly one of the loveliest things in all of physics, and I promise we get there tonight. But I'm not going to just hand it to you now, because it wouldn't land. First, I owe you the cast. Before we can explain how the runt rules the world, you have to actually meet everyone the runt is being measured against.
The cast. All right, I'm sold. Introduce me. So how many are there? How many of these forces are we actually talking about, all told?
4. That is it. That's the entire list. As far as we know, and I'm going to keep saying that, as far as we know, because it's the honest thing to say, there are exactly 4 forces in all of nature. 4 ways, and only 4, for anything anywhere to push, or to pull, or to bind onto anything else. 4 ways for one thing to reach out and lay a hand on another.
4. That feels almost insulting small. That's it? Everything? Every push, every pull, every stick together and every fly apart in the whole universe, from all of history, out of 4.
Out of 4. Think of the single most complicated thing you can dream up. A thunderstorm splitting the sky, a heartbeat, a supernova tearing itself to shreds, a single quiet thought crossing your mind right now. Every one of those, all the way down to the bottom, is nothing but these 4 forces at work. 4 or fewer. Take any event anywhere in the universe and pull it apart far enough. Keep pulling, and there is nothing left underneath but some mix of these same 4, doing the only 4 things they know how to do.
So this is genuinely the complete set, not the 4 we happen to have studied the most, the whole shelf, nothing hiding behind the others.
The whole shelf, to the very best of everything anyone has ever managed to test. And here's the friendly part, the part that makes this easy. You've already met 2 of the 4. You've known them intimately your entire life. So let's start there, with the 2 old friends. Get comfortable, and then I'll introduce you properly to the 2 you have genuinely, truly never met.
The 2 old friends first. Good. Give me the first one, and I'm going to guess, from the last 10 minutes, that it's our little runt.
It's the runt. Gravity. And gravity got its first honest description from Newton, and the great shock of what Newton saw was that it isn't a special Earth thing at all. The very same pull that drops an apple off a branch is the pull that swings the moon around the sky. One law doing both. Every mass in the universe pulls on every other mass. Always, everywhere, no days off. You pull on me, right now. The Earth pulls on the moon. A star you'll never see pulls, ever so faintly, on you. Every lump of stuff tugs on every other lump of stuff. That, in one sentence, is gravity.
Every mass pulls every other mass. So right this second, I'm being gently tugged at by, what, the coffee cup sitting on my desk?
You genuinely are. And by the wall, and the chair beneath you, and the person on the far side of the room. All of it pulling on you, this very instant, from every direction at once. You don't feel a whisper of it, because next to the Earth's enormous pull, it's laughably, unmeasurably tiny. But it is real, and it never once switches off. That's the first friend. Now the second, and this one is the workhorse of your entire waking day. Electromagnetism.
Electromagnetism. And right away that name sounds like 2 completely different things clumsily bolted together. Electricity and magnetism, like somebody couldn't make up their mind and just kept both.
And that clumsy double-barreled name is hiding the whole triumph. That's the lovely bit. For the longest time, they really did look like 2 separate things. Electricity over here, magnetism over there, and then light off in some third box entirely, apparently nothing whatever to do with either of them. And it was Maxwell who proved they were never separate at all, not for a moment. Electricity, magnetism, and light are one single force wearing three different costumes. One thing. That awkward long word is quietly trying to tell you that every time you say it.
And that's genuinely not a small thing to have spotted. That light itself is only that same force out travelling.
It stopped the whole world cold. Light had been its own separate riddle for all of history, and nobody had dreamed it was merely electromagnetism on the move. Maxwell followed the sums honestly, and out fell light, uninvited.
So the spark off a doorknob, the compass needle swinging north, and a beam of sunlight through the window. Those are all one and the same force underneath.
All the very same force underneath. And let me tell you how much of your ordinary life this one runs, because it's almost everything. Every push you have ever felt in your life that wasn't gravity, every single one of them, was this force. Your hand pressing on the table, and the table stubbornly pushing back. The chair holding you up instead of swallowing you. The floor refusing to let you sink through it. A handshake, catching a ball. All of that solidity, every touch you've ever felt, is electromagnetism. Gravity pulls you down toward the center of the earth. Electromagnetism is the thing standing in the doorway that stops you actually falling all the way there.
Hold on though, the floor holding me up is a magnet thing? Because that is really not the picture that jumps to mind when someone says the word magnet.
Not a fridge magnet thing, no, but the very same force underneath the fridge magnet. When your foot presses down on the floor, the thing that actually stops it going any further is the electrons in your foot shoving against the electrons in the floorboards. And that shove, that refusal, is electromagnetism. Every so-called solid surface you have ever leaned your weight on is really that one force, quietly saying no. So there they are, your two old friends, gravity and electromagnetism. And now, at last, the two strangers.
The two I've never met, and you keep saying never met in this pointed way, like it's somehow their fault, like they've been dodging me at parties for years.
They rather have been, honestly. And here's exactly why you've never met them. These next two forces are entirely real, and they're doing utterly crucial work every single second of your existence. And yet you have never once felt either of them directly, not for an instant, in your whole life. And the reason is simple and a bit comic. They never leave the atom. They only act across distances smaller than the tiny core of a single atom, and past that, nothing. They just stop. They switch clean off. They are, the pair of them, complete shut-ins.
Shut-ins, forces that will not leave the house.
Forces that will not so much as come to the front door. And the first of the two is the one that beats gravity so badly it's almost unkind to watch. The strong force. It is the strongest thing in all of nature, by a distance, but it lives its entire life inside the little core at the center of the atom, and it never, ever comes out into the open. All that raw power sealed up in a room far too small for you to ever see into.
So the mightiest force there is spends its whole existence in hiding, and we'd never guess it was there just by looking around.
Never. You could study the world your whole life with your eyes and never suspected. It leaves no mark you can see. We only know it's down there because, without it, matter itself comes undone.
The strong force. Named, I can only assume, by a committee that had used up all its imagination earlier that same afternoon.
The naming does get a bit blunt down at this level, it's true. But it does precisely what the label promises. It's the strong one. It's the glue holding the very core of every atom together. And we'll get to exactly how it manages that. And then there's the fourth, the last one, the genuine oddball of the whole family, the weak force. Also a shut-in, also never leaves the atom. But where the strong force is all about holding things together, the weak force does something far, far stranger than that. It changes things. It reaches in and turns one kind of particle into a completely different kind.
It changes them. Into what exactly? Turns them into what?
We'll get there, and I promise it's the strangest job of the whole four. For now, just shake its hand and remember its face. Because that's the family. That's everyone. Gravity, electromagnetism, the strong force, the weak force. 4 ways for anything to touch anything, and there is no 5th one waiting in the wings. That, right there, is the entire toolkit the universe reaches into to build absolutely everything it has ever built.
4. 2 of them that reach out into the wide world, and 2 that will not step outside the atom. And that's everything. Storms and stars and me, and the thoughts in my head. All of it from those 4.
All of it. Every last bit. And now that you've actually met the 4 of them, we can finally do the thing that makes this whole night click into place. We can line them up, shoulder to shoulder, and rank them. By raw muscle, pure strength, strongest down to weakest, no mercy.
Oh yes, now we settle it properly. Now we find out who actually wins the arm wrestle. Line them up, strongest first, and let's go.
Right. At the very top of the ladder, no contest, no debate, the undisputed champion, the strong force. It is the mightiest force in all of nature, full stop. Nothing else even comes near it. When the strong force takes hold of something, it grips, like nothing else in creation can grip.
Top of the ladder, the strong one. Fits the name at least. And directly below it?
Below it, and already a real, noticeable step down, comes electromagnetism, your workhorse. The force of every touch, every spark, every beam of light. Now it's genuinely mighty in its own right, but set it next to the strong force and it's plainly the weaker of the 2, feebler by a solid margin. Think of it as the champion's smaller, scrappier sibling.
So there's a gap already. Strong on top, then a clear drop to electromagnetism in second. Keep going down.
Then down another step, feebler again, the weak force. And this one has thoroughly earned its name. It's weaker than electromagnetism by a good long stretch. That's 3rd place on our ladder, and notice, by now we've already come down quite some way from the champion sitting up at the top.
Strong, then electromagnetism, then the weak force. And in dead last place. Well, I've known this one since the paperclip jumped.
And now brace yourself properly, because this last step down is not a step at all. It's a cliff. Underneath the weak force, far, far below it, below every single one of them, sits gravity. And the drop from the weak force down to gravity is nothing like the tidy little stairs we've just been walking down. It is a plunge. Gravity is weaker than the rest by an amount so vast that it genuinely stops behaving like a number you can hold.
All right, give me the size of it then. How much weaker? Put it in something, anything that I can actually get my hands around.
And here's the honest trouble. I can't put it in an ordinary comparison because there is no ordinary comparison big enough to do the job. The strong force outmuscles gravity by a figure with more zeros trailing off the end of it than you could read aloud in a single breath. Not 10 times stronger, not 1,000 times, not 1,000,000 times. A number so long that if I started reading the zeros off it aloud right now, we would still be sitting here reading zeros when this episode was meant to end.
That can't be a real number. That isn't a difference in strength anymore. That's a difference in kind. Those 2 things barely belong on the same chart.
They very nearly don't. And now comes the moment where it all pays off, because you have already seen that impossible number with your own 2 eyes. The paperclip. The fridge magnet lifting that clip clean off the table against the entire pull of the planet Earth. That was electromagnetism against gravity, head to head. And electromagnetism won so easily it never even noticed the contest. That little jump off the tabletop. That was this cliff made visible right there on your desk. One cheap magnet casually beating a whole planet is what an unspeakable gap in strength actually looks like out here in the real world.
So when that clip jumped, I wasn't really watching a magnet being strong at all. I was watching gravity being pathetic.
That's a genuinely cruel way to put it, and it is precisely right. The magnet isn't especially strong. Gravity is simply that weak. The clip jumped because even a feeble little magnet, drawing on a force so enormously mightier than gravity, wins that particular tug-of-war before it has even properly begun. The whole Earth turns up for the contest and loses to a coin-sized scrap of metal because the only muscle the Earth had on its side of the rope was the runt.
Okay, so now the wall I ran into at the start is twice as tall as it was. Gravity is the weakest, laughably, unreadably, cliff-droppingly weakest of the four, and yet somehow gravity is the one shaping the stars and the galaxies and the entire visible universe. That is not a small puzzle anymore. That's a full-blown scandal.
It's a proper scandal, and you've laid it out perfectly. The strongest force builds nothing you can see up in that sky. The weakest force builds all of it. So what we have to do now is explain how on Earth the runt ends up running the cosmos. And there are exactly two reasons, two clean and gorgeous ideas, and honestly each one on its own would make the trip worth it. Let's take them one at a time, carefully. And the first one isn't about strength at all. It's about how far each force can reach.
Reach, as in, how far out into the world you can still feel each one before it fades away to nothing.
Exactly that. Because a force isn't only about how hard it pulls, it's about range. How far away can you get and still feel its hand on you? And on this question, the four of them split cleanly, dramatically, into two camps. Two of these forces reach out forever, and the other two can barely reach across a room the size of an atom.
Forever? You're using that word properly. A force can genuinely reach forever.
Forever, in this precise sense. It fades as you travel further out. It grows gentler and gentler and gentler with every step of distance. But it never quite falls all the way to nothing. There's always the faintest whisper of it still there, however absurdly far out you go. And the two forces that behave this way are the two old friends. Gravity reaches forever. Electromagnetism reaches forever. Those two are the long-range pair.
So the Earth's gravity doesn't just stop politely at the edge of the sky. It carries on out into space, getting weaker and weaker but never actually ending.
It carries on, fainter and fainter, forever but never off. The Sun's gravity reaches right across the whole solar system and holds every planet on its leash. A galaxy's gravity reaches clear across itself and keeps 100,000 million stars turning in slow formation. It thins with distance, always, but it never once truly ends. And it's the same story with electromagnetism. The light from a distant star crosses the entire width of the universe to land at last in your eye on a clear night. That's electromagnetism, still going strong after a journey longer than your mind can hold.
So every time I glance up at a star, I'm catching a force that's been on the road since long before anyone was here to look.
Long before, yes. That light set out an age ago and crossed the whole dark the entire time, and the force carrying it never once faded to nothing. That's what long range really means. It refuses to stop.
All right, that's the two that reach forever, the two I already knew. Now the two shut-ins. What's their range?
The two shut-ins are the exact opposite, and it is genuinely dramatic. The strong force and the weak force reach no further than the width of the little core at the center of an atom, that tiny, dense knot of stuff right at the very heart of things. Out to the edge of that little knot, they are absolutely overwhelming, the most powerful things in nature. One single step past it, and they are simply gone. Not faint, not a whisper. Gone. They switch off as sharply as if somebody had thrown a lever.
So there's a hard edge to them, a cliff edge. Inside the core, all powerful. One step outside and it's nothing at all.
A startlingly hard edge. Picture standing in a room where a sound is so loud it's rattling your teeth, and you take a single pace out through the doorway, and there is perfect, total, ringing silence. Not quieter, silent. That's the strong and the weak forces, deafening inside the atom's core and dead silent one step outside it. Which is the whole reason you have never felt them in your life. They never reach out as far as your fingertips. They finish their entire life's work in a space far, far too small for you to have any hope of noticing.
So they really are the relatives who live upstairs and never once come down. You know they're up there, you hear the floorboards, you never actually clap eyes on them.
That's them to the letter. Busy as anything up there, utterly essential to the whole household, and they never come to the door to say hello. Now, watch what that one fact does to our scandal, because this is where it starts to crack open. Step right back and look at the big stage. A planet, a star, a whole galaxy, the vast, empty gulfs of space between the worlds. Out there, on that stage, which of our four forces are even allowed to take part?
Only the two long-range ones, surely. The strong and the weak can't even reach across a single atom. They're never going to reach across a galaxy. They're stuck at home inside the atoms.
Only two are even in the running. And look who just got disqualified. The strong force, our champion, the mightiest thing in all of nature, is thrown out of the race before the starting gun, because it simply cannot reach past the edge of an atom's core. All that unimaginable power, and out in the wide cosmos, it counts for precisely nothing, because it isn't there. It can't get there. So the big stage belongs entirely to the two forces that reach forever, gravity and electromagnetism. And now the contest we actually have to settle gets a great deal smaller and a great deal sharper.
Right? Because now it's just those two left standing on the stage. Gravity against electromagnetism out in the open. And electromagnetism is the stronger of the two by a serious distance. So why doesn't it just win? Why isn't the whole universe out there being shaped by electromagnetism?
And that is the second idea, and it is the truly beautiful one, so let's take it slowly. Because you're completely right to be suspicious. Out on that big stage, of the two forces still standing, electromagnetism is enormously the stronger. It ought to stroll it. It ought to be the one carving out the shapes of galaxies. And it doesn't. It sits down. And the reason it sits down is the single loveliest twist in this whole story.
Go on then. Why does the stronger of the two survivors just quietly take a seat?
Because electromagnetism comes in two flavors. Two kinds of electric charge, call them plus and minus, positive and negative. And here's the rule you already half remember from somewhere. Likes push apart, opposites pull together. Two pluses shove each other away. A plus and a minus rush together into each other's arms. That, right there, is the whole personality of the force. It comes in two opposite signs, forever squabbling.
Two signs, right, positive and negative. That much did survive from school.
Now follow carefully what those two opposite signs do to you over a big distance. Because two opposite signs means they can cancel each other out. Take a single atom. It's got positive charge sitting in the middle of it, and an exactly equal helping of negative charge out around the edge. From very close up, sure, there's plenty going on, lots of push and pull. But step back just a little way, and the plus in the middle and the minus around the outside blur together and neutralize. They cancel. From any real distance at all, that atom looks, electrically speaking, like absolutely nothing. Perfectly balanced, silent.
So the positives and the negatives sort of smother one another, muffle each other down to nothing.
They smother each other completely. And here's the thing. Very nearly everything in the whole universe is just like that atom. Very close to perfectly balanced, the same amount of plus as minus, the two of them cancelling down to a hush. So now take a whole planet's worth of electromagnetism. All those countless positive and negative charges in near-perfect balance, and across any real distance, the pluses cancel the minuses, and the entire mighty force very nearly neutralizes itself right down into silence. It's like a vast stadium packed with people, half of them roaring push, half of them roaring pull, and from outside the stadium walls, you hear almost nothing at all. Just a faint hum where all that shouting cancelled out.
So, a bolt of lightning is really just electromagnetism for one wild second, forgetting to cancel itself.
That's exactly it. For a heartbeat, the balance breaks. A heap of one sign piles up with nothing to hush it, and the force gets to shout in one direction at last. That flash is the shout. Then the hush rolls back.
So, electromagnetism is strong, genuinely, powerfully strong. It just can't ever commit to a direction. It keeps talking itself out of it. It keeps cancelling itself.
That's it, precisely. It's strong, it just flatly refuses to commit. All that muscle, and out at any distance it mostly ties its own two hands behind its back, because for every plus shouting one way, there's a minus right beside it shouting the other, and the two of them hush each other down to nearly nothing. Now, and here's the turn the whole night has been building toward, ask that exact same question of gravity. How many signs does gravity come in?
You already told me, didn't you? Way back. Gravity only ever pulls. There's no push to it, ever. So, one sign? Just the one?
One sign. Only one in the entire universe. Gravity has no opposite, no negative version of itself, no anti-flavor lurking anywhere. There is no such thing as anti-gravity. There is no lump of stuff anywhere that falls upward. Every single mass in the cosmos pulls, and every single mass pulls the very same way. Inward, together, toward. There is nothing, nowhere, that cancels it. Nothing that pushes back to hush it. Not one thing in all of creation.
So, gravity physically cannot cancel itself out. There's no minus gravity anywhere to smother the plus, because there's no minus at all.
None. There is no minus. And now, feel what that actually means, because this is the whole payoff. Gravity is the feeblest force there is. From any one little lump of stuff, its pull is pathetic, unreadably, unmeasurably tiny. But it never cancels. Ever. So pile up more stuff, and every single scrap you add throws its own tiny pull onto the same pile, all of it pulling the same way, and nothing anywhere ever subtracts. A pebble's gravity is nothing, but a mountain is every pebble in it, added up. A planet is every mountain, added up. A star, a galaxy, every last scrap of matter in the thing, all of it pulling together in the same direction, nothing ever cancelling, and the total just climbs and climbs and climbs.
So, it starts out as the weakest by a mile, but it turns out to be the only one of the four that gets to just add up cleanly forever. Nothing ever cancels it. So it simply accumulates, piles up without limit.
It accumulates without limit. And that, right there, is the whole answer. That's the resolution of everything we started with tonight. Out on the big stage, electromagnetism, the strong one of the two survivors, cancels itself down to a whisper, plus fighting minus to a standstill. And gravity, the runt, the weakling, the outright joke of the four, never cancels, not once, not anywhere, and so across a whole planet or a whole galaxy, the single feeblest force in all of nature adds up and up and up, with nothing in heaven or on earth able to stop it, until it wins the entire sky.
So gravity ends up ruling the universe not because it's strong, It rules because it never quits and it never cancels.
That's the sentence. That's the whole thing in one line. Weakest of them all by an amount you cannot read aloud, and yet the only one that only ever pulls, the only one that can never, ever be cancelled or hushed. The strong force is mightier, but it can't reach out of the atom. Electromagnetism can reach forever, but it cancels itself to silence. And gravity, dead last, feeblest of the four by that unspeakable margin, is the one single force that both reaches forever and never once cancels. So the runt inherits the whole cosmos, not by force, not by strength, by sheer, patient, bottomless stubbornness.
That is genuinely moving, and I did not walk in here expecting a talk about forces to get me there. The weakling wins the universe because it's the one that flatly refuses to stop.
The one that refuses to stop and refuses to be cancelled. Those two things together. Every other force is louder than gravity and shorter-lived out on the cosmic stage. Gravity is the quiet one at the very back of the room who simply never ever leaves. And given a whole universe's worth of time and a whole universe's worth of matter, quiet and never leaves beats loud but cancels every single time it's ever tried. Every time.
Okay, I feel like we've properly cracked the safe. The paradox we opened with is genuinely resolved, and honestly resolved, no sleight of hand. So let's do the fun part now. Let's go round the family one more time and find out what each one actually does with its day. What's the job? What's each force actually for?
Let's do exactly that. A quick tour round the four of who does what, because each one has a completely different day job, and it's only the four of them together that build everything there is. Start at the top with the champion, the strong force, and its job, in a word, is glue. It is the glue at the very deepest heart of matter.
Glue, right. Gluing what to what, exactly?
Two layers of gluing, actually, one inside the other. First, the deep one, and you'll remember from earlier in the season that a proton isn't a single solid thing at all. It's three smaller pieces, the quarks, bundled up tight together. Well, what does the bundling? What holds those three quarks in a knot instead of letting them wander off? The strong force. It's the glue that grips the quarks and refuses to let them go, packing them into every proton and every neutron in existence. That's job one, the deep one. It makes the proton and the neutron in the first place.
So, without the strong force, protons and neutrons don't even hold together. They'd just come apart into a spray of loose quarks and drift off.
They wouldn't exist at all. There'd be no protons, no neutrons, just loose quarks, and no way to build a single thing out of them. And then there's job two, one level up from that. Those protons and neutrons cluster together to make the core of an atom, and, left to their own devices, they could never manage it, because the protons are all positively charged, and electromagnetism is screaming at them at the top of its lungs to fly apart and never speak again. The strong force is the thing that overpowers all that screaming, reaches across, and clamps the protons and neutrons together into one tight little knot anyway. It builds the core of the atom in the teeth of electromagnetism's fury.
So the strong force is actually fighting electromagnetism right there, toe to toe, inside every single atom, and winning.
Winning inside every atom's core, which it can only do because, up that close, it's so very much the stronger of the two. And here's the payoff I want you to feel right in your bones. Without the strong force, you could never have a single thing heavier than the very simplest atom of all. No carbon, no oxygen, no iron, no gold, no salt, no water, no planets, no chemistry, and no you. Everything in the universe that's even remotely interesting is heavier atoms, and every single heavier atom is the strong force, holding its core together against the odds, moment by moment.
Moment by moment, so it isn't a one-off gluing at all. It has to keep holding forever, or the whole thing lets go.
Forever, every instant. Take it away for one heartbeat and every core in your body would burst apart from the proton's own shoving. It doesn't glue once and wander off. It holds in every atom of you without a pause.
No strong force, no anything worth mentioning. Understood. Next up, electromagnetism, the workhorse. What's on its list of jobs?
Electromagnetism's list is, more or less, your entire life. Start back at the atom again. The core is positive, and out around it sit the electrons, which are negative. And what holds those electrons onto the atom keeps them circling round instead of just drifting off into the void. Electromagnetism. Opposites attract. The negative electrons are held fast to the positive core. So electromagnetism is the force that builds the whole outer part of every atom.
So the strong force does the tiny core, right at the center. And then electromagnetism takes over and does everything from the core on outward.
That's the handover, beautifully. The strong force builds the core. Electromagnetism builds everything outward from it. And once electromagnetism has built the atoms, it doesn't stop there. It's the force that hooks atoms together into molecules. Every molecule in your body, every drop of water in the sea, is just atoms bonded to atoms by electromagnetism. It's the force that makes matter feel solid, like we said. It runs the entire whole of chemistry. Every reaction, every fire, every rusting nail, every single breath you take is electromagnetism rearranging who is bonded to whom. And on top of all of that, it carries light. Every color you have ever seen in your life is this one single force arriving at your eye.
So, chemistry and solidity and all molecules and all of biology and light itself, that's all one force. The entire texture of ordinary life is electromagnetism.
Very nearly everything you would ever think to call every day is this one force. Gravity holds you down onto the planet, and electromagnetism does essentially all the rest of your waking experience. Now, third, the oddball, the weak force. And this one's job is genuinely peculiar, properly unlike the other three.
Right, you've teased this twice now. The other three either hold things together or shove things around. This one changes things.
It changes them. The strong force and electromagnetism are all about holding and pushing, binding stuff up, moving stuff around. The weak force does something no other force in nature can do. It reaches right into a particle and turns it into a different kind of particle altogether. It can take one type of particle and transform it, change its very identity, into another type entirely. It's less a glue and more an alchemist.
An alchemist. It genuinely turns one kind of particle into another kind? That's just allowed? Nature permits that.
It's the weak force's whole speciality. It's the only thing in nature that does it. And before that sounds like a pointless little party trick with no consequences, let me tell you the single most important thing it does. You know the sun is up there, pouring out light and warmth, keeping this entire planet alive and green. That light comes from the sun, fusing tiny particles together deep in its core, step after step, releasing a flood of energy each time. And the very first step of that whole long chain, the step that gets the sun's fire lit in the first place, can only happen because the weak force reaches in and changes one particle into another. No weak force, no first step. No first step, no fusion. No fusion, no sunlight.
So that feeble little force, that shut-in that never once comes downstairs, is the reason the sun shines on us.
The reason the sun shines. That feeble little identity changer, locked away inside the atom, strikes the match on the reaction that warms the entire solar system. It's the smallest job done in the loudest possible way.
So the sunlight on my face this morning really started with that shy, hidden little force, flipping one particle into another, deep in the sun.
Every last beam of it, each ray you've ever felt traces back to that one shy little force deep in the sun's core, changing a particle's identity to strike the first match. The shyest little force there is, keeping a solar system warm. Now, last of the four, the runt, our hero of the evening, gravity. What does gravity actually do when it's at home?
Gravity does the big stuff. We've basically said it already tonight, haven't we? The stars, the galaxies, all the huge things.
The big and the slow, all of it, top to bottom. Gravity shapes the large-scale world. It gathers loose gas into stars and then lights them by crushing their cores until they ignite. It holds planets steady in their orbits and moons wheeling around their planets. It winds 100,000 million stars up into a single galaxy and then holds that galaxy together for ages beyond any counting. And on the small end of its work, it's also the very plainest thing you know. It's the apple dropping off the branch. It's the long arc of a ball thrown across a field. It's the moon, hung up there in the sky, falling around us forever and somehow never once landing.
So the very same force is both the falling apple and the wheeling galaxy. That's Newton's whole point, right there again.
Newton's whole point, precisely. The apple and the moon obeying one single law, and that one law reaching all the way out to move the galaxies. So there's the family, and there's the division of labour between them. Strong force builds the cores of atoms. Electromagnetism builds atoms, molecules, chemistry, solidity, light, the whole everyday world you live in. Weak force changes particles and lights the sun. Gravity shapes the large and the slow. 4 forces, 4 jobs, and between the 4 of them, that is the entire working of everything there has ever been.
When you lay it out flat like that, it's almost unnerving how complete it is. 4 little machines, and they build the whole universe between them and never ask for a fifth. There's something genuinely wonderful about how few there are.
There really, truly is. Whatever you happen to be looking at, a raindrop on the glass, a nebula 10,000 light-years off, the back of your own hand, it is some collaboration of exactly these 4, and no others working together. That's the map, complete. And I want to spend our last little while on where this map is actually taking us next. Because naming the 4 and ranking them and handing out the jobs, that's only the very beginning of the season, not the end of it.
So this has all been the map then. Where does the road actually go from here? What's the big question we go chasing next?
Here's the question that's going to drive everything ahead of us, and it's a genuinely strange one the moment you say it out straight. Every one of these 4 forces acts across a gap. Go back to the very start. The magnet pulled the paperclip without ever touching it. There was empty air in between, and the pull crossed it anyway. The sun holds the Earth across an ocean of empty space. The strong force grips quarks that aren't quite touching each other. So the real question, the one sitting underneath all 4 of them, is this. How? How does a force reach out across a gap and push or pull on something it isn't actually touching?
I genuinely hadn't thought to even ask that. The magnet just does it. It reaches out across the nothing and grabs the clip. But how does anything reach across nothing?
That is the deep question, and it's the one we're going to chase force by force for the rest of this whole season. For each one, we'll ask the very same thing. What actually carries it across the gap? What's the messenger running between the 2? Because here is the astonishing part. 3 of the 4 forces have an answer to that question, and it's the very same shape of answer for all 3, and it sounds completely, certifiably insane the first time you hear it. And it is true, every word of it.
The same answer for 3 of the 4, and it sounds insane. And you are absolutely not going to tell me what it is tonight, are you?
Not tonight, but I'll give you this much to carry away. Each of the forces has its own messenger, a particle that carries it across the gap, and we'll meet them one at a time, properly, over the coming episodes. Electromagnetism's messenger, you already know the name of it. It's the photon, the particle of light itself. And how a messenger like that manages to carry a push or a pull across a stretch of empty space is one of the strangest and most wonderful ideas in the whole of physics. That's exactly where we're headed next.
And the photon, that's not some brand new thing you're springing on me. That's the light itself that we've been talking about all hour.
The very same. The particle of light and the messenger of electromagnetism are one and the same. Every push you feel and every colour you see is ferried by that one messenger. We just hadn't said the word until now.
3 of the 4 have this messenger idea, which means one of the 4 doesn't fit. And I've got a horrible feeling I already know precisely which one you're about to name.
You know exactly which one. 3 of the 4 fall neatly into line. The strong force, electromagnetism, the weak force, each with its own messenger, each one slotting into the same clean picture. And then there is gravity, the runt. It won't fit. Gravity is the holdout.
The holdout? Of course it is. It can't even lose an arm wrestle with a bit of dignity. And now it won't join the club the other 3 formed either. Typical.
It won't. And I want to be completely, flatly honest with you here, because this is a real edge of what we know, not a neat and tidy one. For the other 3, we have this beautiful picture of a messenger particle carrying the force across the gap. And it works, gorgeously, exactly, every time we check it. For gravity, we've imagined that there ought to be a messenger too, some particle that carries the pull across the space. And we have never found it. Never caught so much as a glimpse of one. Never seen it. The picture that fits the other 3 so perfectly has simply never clicked into place for gravity.
So it's not that you're saving the answer up for a later, more dramatic episode. It's that, honestly, there isn't one yet.
There isn't a settled one. It is a genuine open frontier, a loose thread hanging right off the edge of this whole beautiful map. We can fit 3 of the 4 forces into one clean quantum picture, particles carrying forces back and forth. And gravity, of all things, the very force you feel the most, the one holding you in your chair, the one that runs the entire cosmos, is the one we still can't fit in. It's the honest whole sitting right in the middle of the beautiful thing.
That is such a strange place to end up standing. The single most familiar force there is, the one holding me down in this chair right now, is the one that physics, deep down, understands the least well of the 4.
It's a properly humbling thing, and I would far rather leave that thread hanging honestly in front of you than tie it off with a comforting little lie. There is a deeper story about gravity, a completely different way of seeing the whole thing, where it isn't really a force reaching across a gap at all, but instead something about the very shape of space and time being bent and curved by the matter sitting in it. That's Einstein's picture of gravity, and it is magnificent. And it belongs to a whole other course than this one. So one line, and no more than one. Gravity may not be a force in the same way the other 3 are at all. We'll respect that thread. We just won't pull on it here.
Fair enough. So we leave gravity standing a little apart from the other 3, the beautiful holdout, the one that won't come inside. So where does all that leave us for next time?
It leaves us with the 4 forces named and ranked, and each handed its job, the whole map drawn out and coloured in. But not the mechanism, not the how. We now know what all 4 of them do. We do not yet know how any single one of them reaches out across a gap in order to do it. And that, right there, is the whole of next time. And it is, I think, the strangest mechanical idea in the entire subject.
Give me the shape of it, at least. Just the shape. What's the strange idea?
The strange idea is this. A force, a push, a pull, any of it, is really just particles playing catch. Two things acting on one another by constantly, endlessly throwing tiny particles back and forth between them. Electromagnetism, the force behind every single touch you have ever felt, turns out to be two charges tirelessly tossing photons at each other, back and forth, and back and forth. And somehow, out of that daft little game of catch, comes the push.
Throwing things back and forth makes a push? Okay, I can just about picture that much. If I hurl something good and heavy at you, you get shoved backwards, sure, I'll grant you that. But that only ever does pushing, doesn't it? How on earth do you pull something toward you by throwing things at it? That's madness. That's not how any of it works.
And that exact madness is precisely where we start next time. How a simple game of catch can pull two things together just as easily as it shoves them apart. And there's one last lovely catch sitting on top of the whole thing. The little particles doing all the throwing aren't quite real. Not real in the way you and I are real. But that, mercifully, is next episode's problem, and not tonight's.
Particles that carry every force in the universe, and also aren't quite real. That is a wonderful place to be left dangling. So, 4 forces, one gorgeously resolved paradox, and a runt that ends up ruling the whole sky purely by refusing to ever give up. I'll take all of that, gladly. Next time, how to push something by throwing things at it, and the far stranger trick of somehow pulling. I'll be right here for that one. See you then.